to the second part of the lecture on basic fundamentals of AC machines. In the previous lecture, we have already discussed the types of AC machines and three-phase induction motors in details covering the construction, working and speed control. Myself, Dr. Shrimpi Ralhan, Professor Shri Shankaracharya Technical Campus, Bhilai. In today's lecture, we will explore the fundamental principles of single-phase induction motors, working principle and their characteristics. We will also see the types of single phase induction motor depending on the starting methods which are used to start them. We will also have a look on the synchronous alternators and motors in brief. Today we are diving into an essential component that powers many of the conveniences and necessities of modern life, the single phase induction motor. Let's explore how these motors play a crucial role in our daily activities. Single phase AC supply is the standard in homes and many other buildings across the globe. This leads us directly to the single phase induction motor. Due to the universal presence of single phase AC supply, these motors are ubiquitous in numerous devices. From household to commercial settings, they provide the necessary mechanical power for countless applications. Considering the variety of applications, everything from your kitchen blender and office air conditioners to pumps and tools in workshops, these motors are integral to the functioning of vast array of equipment. As we see, single phase induction motors are embedded in various applications. Whether in a home appliance or an office equipment, they are silently working behind the scenes to make our lives easier. So, the basic working principle of single phase induction motor has to be discussed here. The fundamental principle of single phase induction motor is based on the electromagnetic induction. For torque generation, two interacting magnetic fields are required. The stator winding carries an alternating current which produces the flux, which is also alternating in nature, and this flux is known as the main flux. This main flux interacts with the rotor, inducing an electromotive force or EMF due to transformer action. This induced EMF drives a current in the rotor, resulting in the creation of rotor flux. Thus, second flux is produced according to induction principle due to induced EMF, hence the motor is called induction motor. In contrast to DC motors, if we see our induction motor, the DC motors rely on separate electrical supply for the field winding and the armature to produce the necessary interacting fluxes. So, here is the highlight, that is a key difference between DC and single phase induction motor. DC motors are inherently self-starting, whereas single phase induction motors are not, and this is due to the lack of initial rotor flux at startup. So, if we see the torque speed curve of a single phase induction motor, it shows the relationship between the motor's torque output and its speed. The torque produced by the two opposite rotating flux components are exactly opposite to each other. At startup, when the rotor is stationary, the motor develops no torque, which is why it cannot start on its own. The reason for this lies in the nature of single phase power. Unlike three phase motors that naturally create a rotating magnetic field, single phase motors produce a pulsating field. This means that at zero speed, the induced rotor currents cannot produce the required torque to overcome the static friction and inertia. This very inability to self-start is important characteristic that impacts how these motors are used in various applications. So here comes into picture double revolving field theory. To address the self-starting limitation, we can turn to the double revolving field theory, which provides the explanation of single phase motor operation. According to this theory, a single alternating magnetic field can be resolved into two rotating fields, each rotating in opposite directions but with equal magnitude. As you can see, FF and FB are the two rotating fields in the forward and the backward directions, respectively, rotating with equal speed. These two fields interact with the rotor conductors, inducing the currents that create additional magnetic fields. The net torque is the result of these interactions, but at zero speed they cancel each other, explaining the lack of starting torque. So, this illustration helps us to visualize how a single field can be conceptualized as two separate rotating fields, each contributing to motor's operation once started. As we have been discussing that the single phase induction motors are not self-starting. So, what is the reason why single phase induction motors are not self-starting? Let us see in detail. The single phase supply creates a pulsating magnetic field which results in no net starting torque. To make the induction motor self-starting, it is necessary to produce a rotating magnetic field, and in order to do so, there should be at least two magnetic fields, and these two magnetic fields should satisfy the following condition. The magnetic fields should be shifted by 90 degree with respect to each other in space, that is, one flux is horizontal, then the other one should be vertical. Also, these two magnetic fluxes should be in time quadrature. If the fluxes are represented by the phasor must be 90 degree with respect to each other. So, a single phase stator winding cannot satisfy these two conditions because a single winding can produce only one flux. Hence, the modification as we have discussed earlier. So, let us discuss now the starting and running performance of single phase induction motor. On the basis of the starting methods, the different types of single phase induction motors are split phase motor or resistance start motor, capacitor start motor, capacitor start run motor or two value capacitor motor, and the permanent split capacitor motor or single value capacitor motor, and the shaded pole motor. So, let us see each one by one. Split phase motor or resistance start motor. This motor consists of two windings, namely main winding and the auxiliary winding. The main winding is highly inductive in nature and the auxiliary winding has high resistance which is added in the series, as you can see. The current flowing through the main winding is Im, which lags behind the voltage V by some angle, as you can see from the phasor diagram, because the main winding is highly inductive in nature. Similarly, the current flowing through the auxiliary winding taken as Ia is almost in phase with the voltage V, as you can see from the phasor, because the auxiliary winding is resistive. So, the fluxes produced by these two currents will be placed at approximately 90 degree from each other, and the resultant of these fluxes will produce rotating magnetic field, and due to this rotating magnetic field, torque will be produced. Switch is connected in series with the auxiliary winding to get automatically opening the circuit when the rotor speed reaches about 70% of the synchronous speed. After that, the motor rotates only on the main winding. Thus, under the running condition, the auxiliary winding remains out of the circuit and the direction of the rotation of the split phase motor can be reversed by reversing the terminal of either main winding or the auxiliary winding. The torque speed characteristics of a split phase induction motor is shown. The starting torque TST of the split phase induction motors is poor, that is about 1.25 to 1.5 times of the full load torque. The centrifugal switch opens at a speed n is equal to n naught, and for the speeds above this the motor operates only on the main winding. The starting torque is proportional to the angle alpha. These motors have a poor starting torque and they are preferred in the applications such as fans, blowers and centrifugal pumps. Capacitor start motor is very simple one. It requires only auxiliary winding placed at a space angle of 90 degree from the main winding. It does not need anything except for a centrifugal switch, as the auxiliary winding is used as a starting winding. But the main problem is low starting torque in the motor. As this torque is function or related to phase difference angle between the currents in the two windings, to get high starting torque, the phase difference required is 90 degree. This can be achieved by having a capacitor in series with the auxiliary winding, which increases starting torque and results in additional cost also. The construction of this motor is similar to that of a split phase type motor. The auxiliary winding connected in series with the capacitor draws a leading current, while the main winding continues to draw the lagging current. The current flowing through the main winding Im lags behind the voltage V by some angle, as you can see in the phasor, because the main winding is highly inductive. But the current flowing through the auxiliary winding Ia leads the supply voltage V by some angle due to the presence of capacitor. Hence, the angle between the two fluxes produced by Im and Ia will be large. Due to this large angle, the starting torque produced by the capacitor start motor is high as compared to that produced by the split phase induction motor. When speed reaches 75% to 80% of the maximum speed, the switch opens automatically and auxiliary winding along with the capacitor goes out of the circuit, and induction motor then runs only on the flux produced by the main winding. Applications of this motor due to its high starting torque are in grinder, compressor, conveyors, refrigeration, fan, air conditioning, etc. The third one is capacitor start and capacitor run motor. The two capacitors are connected in parallel at starting. In order to obtain a high starting torque, a large current is required. So, the capacitive reactance X in the starting winding should be low, as the value of Cs should be large, where Cs is our starting capacitor. During the normal operation, the rated line current is smaller than the starting current. Hence, the capacitive reactance XR should be large. Hence, CR should be small, which is our running capacitor. As motor reaches the synchronous speed, the capacitor Cs is disconnected by the centrifugal switch. The capacitor CR is permanently connected in the circuit and is the run capacitor. So, the role of capacitors is very important here. The capacitor always remains in the circuit and it decides the performance of the motor at the time of starting as well as the time of running. The selection of the value of capacitors is a compromise between two factors, high starting torque and better running performance. This is very important in this type of motor. The applications, if we look at, due to high starting torque, the capacitor start motors are used for grinders, compressors, conveyors, refrigerations, fan, air conditioning, etc. Next is our shaded pole motor. The shaded pole induction motor is usually a squirrel cage motor. Every stator pole is divided into two parts by keeping a small split in the pole face, and the smaller portion is covered with a thick short circuited copper band or shading band. When the stator winding carries current, the main pole produces a flux phi m. Thus, flux links with the shading band and this band acts as a shorted secondary, stator winding being its primary. The circulating current induced in the band produces another flux phi sp. At the instant t1, the current is increasing, as you can see from the figure. The induced EMF tries to oppose it, thus flux phi s and the resultant are flux in the unshaded part. At instant t2, current is almost constant, induced EMF and flux phi s are negligible. Resultant flux is almost at the center of the pole, thus it has shifted its position. At instant t3, current is decreasing, the induced current and flux phi s try to oppose this decrease. Hence, there is a crawling of flux in the shaded part and the resultant flux lie in the shaded part. This action continues and resultant field rotates from unshaded part to shaded part. Hence, the rotor also rotates in the same direction. The direction of rotation cannot be reversed unless the position of the shaded ring is changed from one part of pole to another part of pole. Such a motor develops low starting torque and it has a low power factor. However, this is cheaper in cost and commonly used in practice, and the applications are in table fans, blowers, washing machines, refrigerators, etc. After discussing the single phase induction motor, let us now look into synchronous machines. Synchronous machines generate AC EMF and operates at constant speed called synchronous speed. And as we know that we can use synchronous machines both as generators and motors. All the modern power stations consist of large capacity 3-phase alternators, and the synchronous motors are used as power factor correctors. If we now look at alternators, there we have a stationary winding known as stator, while the rotating winding is called rotor. The stator is the stationary armature consisting of a core and the slots to hold the armature winding, similar to the armature of the DC generator. The stator core uses laminated construction. The entire core is fabricated in a frame made of steel plates. The core has slots on its periphery for housing the armature conductors. Frame does not carry any flux and serves as a support to the core. So basically our frame is a supporting outermost covering of the machine. Next is our rotor. There are two types of rotors used in alternators. We just had an introduction about it in the previous lecture when we have discussed about the types of machines. So the two types of rotors are our salient pole type and cylindrical type or non-salient pole. In salient pole type rotor, the projected pole type of poles are used. They are attached from the surface of the rotor. The poles are built up of thick steel laminations and they are bolted to the rotor. The pole face has a specific shape. The field winding is provided on the pole shoe. These rotors have large diameters and small axial lengths. The limiting factor for the size of the rotor is the centrifugal force acting on the rotating member of the machine. As the mechanical strength of the salient pole type is less, this is preferred for low speed alternators ranging from 125 rpm to 500 rpm. Such low speed turbines are also known as hydroelectric turbines. The prime movers used to drive such rotors are generally water turbines and IC engines. Now let us see the cylindrical type or the non-salient pole type. The cylindrical type is also known as the non-projected pole type of rotor. The rotor consists of smooth solid steel cylinder having number of slots to accommodate the field coil. The slots are covered at top with the help of steel or manganese wedges. The unslotted portions of the cylinder itself acts as the poles. The poles are not projecting out and the surface of the rotor is smooth, which maintains the uniform air gap between the stator and the rotor. The rotors have small diameters and large axial lengths here. So this is to keep the peripheral speed within the limit. The main advantage of this type is that these are mechanically very strong and hence they are preferred for high speed alternators ranging between 1500 to 3000 RPM. So you can see the difference between the two. Such high speed alternators are called turbo alternators. The prime movers used to drive such type of motors are generally steam turbines, electric motors, etc. Let us see now the working principle of the alternator. An alternator operates on the same fundamental principle of electromagnetic induction as a DC generator, that is, when the flux linking a conductor changes, an EMF is induced in the conductor. Like a DC generator, an alternator also has an armature winding and a field winding, but there is one very important difference between the two. In DC generator, the armature winding is placed on the rotor in order to provide a way of converting alternating voltage generated in the winding to a direct voltage at the terminals through the use of rotating commutator. The field poles are placed on the stationary part of the machine. Since no commutator is required in an alternator, it is usually more convenient and advantageous to place the field winding on the rotating part, that is rotor, and armature winding on the stationary part, that is stator. An alternator has 3-phase winding on the stator and a DC field winding on the rotor. This DC source called exciter is generally a small DC shunt or compound generator mounted on the shaft of the alternator. Thus, the rotor winding is energized from the DC exciter and alternate north and south poles are developed on the rotor. When the rotor is rotated in anti-clockwise direction by the prime mover, the stator or armature conductors are cut by the magnetic flux of rotor poles. Consequently, EMF is induced in the armature conductors due to electromagnetic induction. The induced EMF is alternating since north and south poles of rotor alternately pass the armature conductors. The direction of the induced EMF can be found by Fleming's right hand rule and the frequency is given by the expression shown. The magnitude of this voltage induced in each phase depends upon the rotor flux, the number and position of conductors in the phase and the speed of the rotor. When rotor is rotated, a 3-phase voltage is induced in the armature winding. The magnitude of the induced EMF depends upon the speed of rotation and the DC exciting current. The magnitude of EMF in each phase of the armature winding is same. However, they differ in phase by 120 degree apart in space and time. So, let us, after discussing the alternator, see the working principle of synchronous motor. Synchronous motor works on the principle of magnetic locking. When two unlike poles are brought near each other, if the magnets are strong, there exists a tremendous force of attraction between two poles. In such a condition, the two magnets are said to be magnetically locked. If now one of the magnets is rotated, the other also rotates in the same direction with the same speed due to the force of attraction, that is due to magnetic locking condition. The principle is shown schematically. You can have a look at it. So, to have the magnetic locking condition, there must exist two unlike poles and the magnetic axis of the two must be brought very close to each other. Consider a 3-phase synchronous motor whose stator is wound with two poles. The two magnetic fields are produced in the synchronous motor by exciting both the windings, stator and rotor, with 3-phase AC supply and DC supply respectively. When 3-phase winding is excited by 3-phase AC supply, then the flux produced by three-phase windings is always rotating type. Such a magnetic flux rotates in space at a speed that is synchronous speed, and this magnetic field, called as rotating magnetic field, creates the effect similar to the physical rotation of the magnets in space with synchronous speed. So, the stator of the synchronous motor produces one magnet which is as good as rotating in space with synchronous speed. The synchronous speed of a stator rotating field depends upon the supply frequency and the number of poles for which the stator winding is wound. If the frequency of AC supply is F Hertz and the stator is wound for P poles, then the speed of the rotating magnetic field is synchronous, given by Ns is equal to 120 F by P. In this case, the stator is say wound for 2 poles with 50 Hertz supply. The speed of the rotating field would be 3000 RPM. This effect is similar to the physical rotation of 2 poles with a speed of Ns RPM. For, let us say, for the simplicity of understanding, we assume that the stator poles are N1 and S1, which are rotating at a speed of Ns. The direction of the rotation of rotating field is say clockwise. When the field winding on the rotor is excited by DC supply, it also produces 2 poles. Assuming the rotor construction to be also of 2 poles, salient type, let these poles be N2 and S2. Now, one magnet is rotating at Ns having poles N1 and S1, while at start the rotor is stationary, that is the second magnet is stationary having poles N2 and S2. If somehow the unlike poles N1 and S2 or S1 and N2 are brought near each other, the magnetic locking may get established between the stator and the rotor poles. As the stator poles are rotating, due to magnetic locking, rotor will also rotate in the same direction as that of stator poles, that is in the direction of the rotating magnetic field with the same speed, that is Ns. Hence, the synchronous motor rotates at one and only one speed, that is synchronous speed. But this all depends on the existence of magnetic locking between the stator and rotor poles. Practically, it is not possible for stator poles to pull the rotor poles from their stationary position into magnetic locking condition. Hence, synchronous motors are not self-starting. So, as our synchronous motors are not self-starting, we need to have some starting methods for starting the motor. This is possible by using various methods such as using the auxiliary motor, using the damper winding as a slip, or running our motor as a slip ring induction motor. Now, let us see one by one what are these methods. If we use the auxiliary motor, in this method the rotor is brought to the synchronous speed with the help of some external device like say small induction motor, and such external device is called pony motor. Once the rotor attains the synchronous speed, the DC excitation to the rotor is switched on. Once the synchronism is established, the pony motor is decoupled. The motor then continues to rotate as a synchronous motor. Next method to start the motor is using a damper winding. In synchronous motor, in addition to the normal field winding, we have a winding consisting of copper bars placed in the slots in the pole faces. The bars are short circuited with the help of end rings. Such an additional winding on the rotor is called damper winding. This winding is short circuited and acts as a squirrel cage rotor winding of induction motor. Next is, as a slip ring induction motor, we can start our synchronous motor. The above method of starting the synchronous motor as a squirrel cage induction motor does not provide high starting torque. So to achieve this, instead of shorting the damper windings, it is designed to form a 3-phase star or delta connected winding. The 3 ends of this winding are brought out through slip rings. An external rheostat then can be introduced in series with the rotor circuit. So when the stator is excited, the motor starts as a slip ring induction motor, and due to resistance added in the rotor, it provides high starting torque. The resistance is then gradually cut off as the motor picks up the speed. When the motor attains speed near the synchronous speed, DC excitation is provided to the motor. Thus, the motor gets pulled into synchronism and starts rotating at synchronous speed. The damper winding is shorted by shorting the slip rings. The initial resistance added in the rotor not only provides high starting torque but also limits the high inrush of the starting current. Hence, it acts as a rotor resistance starter. After discussing the starting methods of the synchronous motor, let us see a very important phenomena which is known as hunting or phase swinging. During the steady state operation of the synchronous motor, a condition of equilibrium is established in which the electromagnetic torque is equal and opposite to load or mechanical torque. In the steady state, the rotor runs at synchronous speed, thereby maintaining a constant value of torque angle delta. If there is a sudden change in the load torque, the equilibrium is disturbed and there is resulting torque which changes the speed of the motor. The phenomena of oscillation of the rotor about its final equilibrium position is known as hunting. Since during rotor oscillations, the phase of the EF changes relative to the voltage Vt, hunting is also known as phase swinging. The term hunting is used to signify that after the sudden application of load or change in load, the rotor attempts to search for or hunt for its new equilibrium position. Hunting occurs not only in the synchronous motor but also in the synchronous generators upon the abrupt change in the loading. Let us see now what are the causes of hunting, what are the effects and how we can reduce hunting. As we have just seen, the sudden changes of the load is the first cause. Now if a fault or sudden change in the supply system takes place, it also leads to hunting. Sudden changes in the field current or field excitation, then cyclic variations of the load torque, the presence of harmonic variations in the load and also in the prime mover torque, they all lead to hunting. The hunting phenomena can lead to loss of synchronism, it can cause variations of the supply voltage, it increases the possibility of resonance, large mechanical stresses may develop in the rotor shaft due to hunting, the machine losses increase and the temperature of the machine also rises, it causes great surges in the current and the power flow. So it is utmost important that the hunting should be reduced by using a flywheel or by using damper windings or by designing the synchronous machine with suitable synchronizing power coefficient or stiffness factor. Damper windings are mostly used for reducing the hunting phenomena. They consist of low resistance copper, brass or aluminum bars embedded in the slots in the pole faces of the salient pole machines. The projecting ends of the bars are connected to short circuiting strips of the same material as used for the bars. With respect to damper windings, rotor behaves as a squirrel cage rotor of the induction machine, that is short circuit due to low resistance. So if the damper windings are added to a synchronous machine for starting, the machine stability increases. In synchronous motor, damper bars reduce hunting and may form the starting winding for the synchronous motors of the salient pole type. For good starting torque, damper bar should have high resistance, but for large damping effect near synchronous speed, the damper bar should have low resistance. Therefore, a compromising between the good starting torque and good damping effect should be made for obtaining the satisfactory operation of the synchronous motor. Not only this, damper bars also play a very important role under steady state operating condition. Steady state operation of the synchronous machine demands that the relative speed between the stator and the rotor field is 0. In other words, the rotor must run at synchronous speed. In steady state, when the rotor is running at the synchronous speed, the relative speed between the damper bars and the rotating air gap flux is 0. Because of 0 relative speed, no flux cutting action takes place and EMF generated in the damper bars is 0. As a result, no damping torque is developed. The damper winding comes into play only during rotor hunting when the rotor speed departs the synchronous speed ns to make the relative speed between rotor and stator field as 0, damper windings operate. As we conclude today's insightful session on the basic fundamentals of AC machines, particularly focusing on single phase induction motors and synchronous machines, let's recap the key points and outline the next steps in our learning journey. We started by exploring the fundamental principles of single phase induction motors, examining their unique characteristics and operational nonsense compared to three phase motors. We have also discussed the various starting methods for single phase induction motors which are critical for their effective operation in different applications. We also introduced synchronous alternators and motors, touching upon their construction, working principles and roles in industrial and power generation settings. Thank you so much.